Great. So today we have two speakers, Red Hat internship projects that were funded last term that will be presenting. I believe that's right, right? Good. And do you want to do an introduction? Or?
Sure. It's my pleasure to introduce Albert. Albert has been working with the group for a while and has managed to get his head around all kinds of internal guts of many of the bizarre things we do. And so this project was sort of a walk on the wild side to see if we could smash together a set of ideas and come up with a realization where we're going to actually really in some sense bastardize Linux to see if we can impose this strange view of a process, but all through user tools.
Good afternoon, everyone. My name is Albert Slepak, and today I will be talking to you about exploring process snapshotting with ForkU. So to give a little bit of a context and background and the motivation for the project, one of the biggest motivators has been the state vector work that Professor Pablo has been doing in his lab for a while, which focuses on capturing the systems or processes state at some instant time, then later using that state to enact all sorts of optimizations. Next is the dynamic privilege project that I'm lucky to have been a part of for quite a while, which gives user space applications the ability to access kernel data structures and kernel memory. And finally, SUSE, the project, the specialized operating system that used state vectors and the mechanism of snapshotting to enact function as a service optimizations. But it was built, it was based on a customized specialized operating system. So what we focused on is on exploring if you could take these three projects and combine them into providing state vector support on just normal Linux. So let's dive in. Imagine that this gray bar is a process. And the initial point at it, if we capture the state of it, we'll call it SV0, state vector 0. And as the process runs, its state obviously evolves. And when we talk about state, it's important to mention we're talking about the memory and the registers of the process. And as the process runs, its state changes, which is represented by the color of the bar. What if we could take instantaneous snapshots of that process's state, underlying states and memory and registers at various points before or after the state changes? And what if we could have a series of these snapshots, or in the future, binary state vectors that we could then feed into neural nets or analyze and compare to see how the process evolves. So what do we actually mean and how do by capturing the state and how do we actually capture the state of the process? What kind of primitives are we talking about here? Well, on Linux, traditionally there is a very familiar system called fork, which allows the parent calling process to create a copy and write clone of its memory layout and to have a child process start evolving and running alongside. But when the control returns to the child process usually starts evolving and running and its state can change. We don't want that. In order to capture the state, we want something like this. We want the parent process to kind of call fork. And when the control returns to the child, we would want the child process to just block indefinitely. That would preserve the state of that parent process at that instant that we could later go back and analyze. So in order to approach this problem, because we can't really change the underlying binary or inject code, we delved into the fork system call anatomy. When you make the user space fork system call, it will go on to the kernel side and call the kernel function kernel clone, which consists of two major parts: copy process and wake up context. It is important to mention that in the Linux operating system, there is a notion of a task, which represents, or as a data structure, task struct, which represents the underlying state of a process. And there's a per-CPU data structure called current task that represents the current running task on a given core. So when kernel clone gets called and copy process gets called, it essentially creates a copy and write clone of the current task. So when we call fork, that would be the parent process's task. But it gets registered in the process table, but it's not yet ready and a state is not yet prepared to get run and scheduled. That's where wake up new task comes in. It actually takes care of all the state preparation.
Sorry, can you just speak up a little bit for us?
It's
Yeah.
hard.
And Wake Up New Task actually takes care of the state preparation and schedules the clone, the child process to get run. But we don't really want that. We want the child process to get blocked and essentially be frozen. So what if we could get rid of Wake Up New Task call and just have the copy process, which would give the blocked state effectively. That is where ForkU interface comes in. New hope. We developed a command line tool that attempts to do that by impersonating another process. We just give it a bit of the target process that we want to fork, and it goes in and uses dynamic privilege to swap or flip its own task struct to be that of the target process and calls fork on its behalf. But instead of calling the entire fork, we also use dynamic privilege and the module out of free build system to only call copy process to get that clone task struct without actually scheduling it. So imagine we have
I
process A.
think you need to just say a word about what you mean by dynamic privilege, because I don't know if everybody knows on this.
So dynamic privilege, and specifically the K elevate mechanism, it allows you to elevate a user space thread to run under kernel privilege, and that gives you access to kernel memory. And additionally, with extra build tools, you can take and call kernel functions from normal user applications. So you write your own hello world, and you can also call a kernel function in there. So what we did is we wrote a user space application that called copy process after switching its own impersonating the task struct, and it essentially called fork on behalf of another process. So as the process A is running, we just give its PID to this ForkU utility, and it created this, what we call a doppelganger process. Doppelganger is this frozen process that is essentially a snapshot of the original process at that instant in time. So why is it useful? We can pass it into another tool that we wrote, snapshot, that took that process and looked at the underlying page table structure. So it didn't introduce anything new. All it did was elevate itself and read the already existing information that is in the kernel about the underlying memory of the process, the page table structure. And it marshaled it into a JSON format and dumped it out to the disk. So we could do this at any point in time when we want to snapshot the original process and create a series of these JSON files. In the future, we want them to be binary state vectors, but these JSON files are also useful. You may ask, why are they useful? Well, on the right side, we have an image of a classic textbook diagram of a page table structure. To me, it looks ugly. It's hard to read, and a lot of people may be unfamiliar. But what we did is we took this JSON file, which is a page table representation of the process, and we built a web tool to visualize it in a more beautiful way, using a radiograph. Each node, starting from the center and going outwards, represents the entries from different levels of the page table, and they're highlighted in green or red based on a heat map system that detects whether the page table entry is 1 or 0. So currently in the screenshot, it's set to execute disable. So all the green nodes are the ones that have execute disable flag set. So they're either read write or read only regions. And the red ones around, they're executable regions. So this is good and all. You can look at the underlying page table, the underlying hardware x86 representation of the page table in a more beautiful way. But the cool thing about the snapshotter tool is that it doesn't have to only work on these doppelgangers. You can also give a live running process to it. And that is what we did. We took a Python interpreter, just spun it up, and took a snapshot. We called that before. And then we allocated a list in Python and added about 200,000 just random integers, strings, Python objects into it to just allocate more memory, and took a snapshot after. These look quite similar, but they're not exactly the same. And if you zoom in into the differences, you can see that an entire new page table directory got added and a bunch of new page table entries. This is really useful when you want to analyze how a certain algorithm affects the underlying hardware, affects the memory, and how it affects the page table structure. You could analyze it and maybe improve it, or take these states and then feed them to a neural net to analyze and improve for later use. So I want to talk a little bit about the current status of the project now. In the ideal world that we were working towards, we wanted to be able to snapshot any process on Linux, and any arbitrary running process at any time. And the doppelgangers that it created, we should be able to control them, kill them. We should be able to use them as templates to spawn running processes in the future. And we want to be able to have a very clear and binary state vector view into them, not just a JSON file. But due to certain limitations like time constraints, there are certain limitations. Currently, we're only capable of snapshotting very simple processes. Well, I should say forking very simple processes, because otherwise the parent process might die. Very simple processes that have no pending signals and are not blocked. So you can't have any IO operations being done at the time when you try to fork your target process. Additionally, when we create these doppelgangers, currently they are in this sort of weird unknown state that we're still exploring and trying to learn more about. We can't kill them, and we can't control them yet. Funny enough, I was testing it out, and I just had like 60 of these immortal Linux processes running that I didn't know what to do with. So I just had to reboot every time. And even though it would be nice to have state vector views, we currently only have these JSON marshal page table representations. But it is a matter of just small programming to get the state vector views working as well. And one of the big new parts that we look forward to exploring as well is the exec-view interface, which would treat these doppelgangers as templates. So you could have a process that got snapshotted at the different times, and each snapshot would be a template to spawn new running instances of that process from that time point, which is, I think, is really exciting. And now I want to talk about some of the challenges that we faced, some big ones, because it turned out to be a lot harder than we initially thought. And the process of actually impersonating another process has been one of the hardest challenges. When you write into current task, it's not as simple, and you have to be very careful about flipping it. You have to write into per-CPU data structures, and those are either protected or what we think processor manipulation is to blame here. We were writing into it, but when reading back from it, we weren't getting the updated value. So that took a while to figure out and get working. Additionally, we also are exploring this, which state the target process needs to be in order for us to fork it. So currently it can't be blocked, no pending signals, no interaction with the IO. And we're trying to get to the point where we have a clear understanding of what state the process has to be in order for us to carefully and safely fork it and snapshot it. And additionally, due to the state of dynamic privilege and the tools we use, such as the kernel module build system, we had to fight through a lot of compilation and linking issues, but we did learn a lot from it, and it's an ongoing. No matter how many challenges we faced, and I would say even because we faced so many different challenges and problems and bugs, we learned so much about the system that we didn't ever expect to learn. And I'm very thankful to have been working on this project and got the opportunity to explore and learn so many new things. Thank you so much for listening. And if you have any questions, yeah.
So can you go back to to where you were showing, you showed the, after the fork, it calls copy process.
Yeah.
So you intercepted the process. So you ended up becoming or pretending that you were that process, and then you ended up just calling the process, like that part of the copy process, or did?
Yes, that is the only function we extracted from this block. Yes.
I see. Okay. So did you stop the process before
So
What was the
what,
target of this? Because if it's already running, then like, there's an assumption whenever copy processing is called that process is called the fork and is stopped.
so that's an excellent question. So one of the constraints that we found is that we made the target process be pinned to the port, say port 0, and our monitor process, the ForkU utility, has to move itself to that port and execute copy process when it knows when the target process is not scheduled currently. So they're on the
Because it's
same-
running.
Right.
Yes, but it is running. It just can't be blocked or have pending signals.
As a matter of fact, the first thing we did do was assume that we don't want to build new tools, so we'll just stop it, send the sig stop,
Yeah,
and then we would do that, but you can't, because fork by definition assumes that it's actually not stopped, right? Because you're actually running when you call fork.
right.
So there's a bunch of checks in here, which we don't know that we actually care about. But in order to just do some exploration, the easier thing to do was to personate it running, which was why this little trick of pinning it to a core, moving yourself to that core, and then taking over curve paths.
That is both very cool and I think a really cool use case for the Elevate functionality. What I'm curious though, so there's obvious limitations of fork by itself for things like multi-threaded programs and things like that. And you said if there's a signal pending, you can't do this. Like what were the key constraints? Were signals you said, or
Right, so copy process, when you look inside, it has a tremendous amount of checks and if statements, which part of the next goal is to explore the example, maybe extracts only certain parts of it. But so it assumes that the parent process called fork and it's currently running. And yeah, we determined that whenever it has a signal pending, then problems occur and either the parent process dies or there's an error that comes up in copy process, so it just returns an error.
that's okay. This is super interesting.
Thank you.
So it's fun stuff. I mean, it got me thinking whether that copy process is actually the right thing to use to do a snapshot, in the sense that what copy process really does, right, is not really a copy. All it's saying is, hey, there's going to be a new process, so it creates a new descriptor and copies the field. But in terms of memory, it actually uses a different dirty trick, which is like setting everything as copy on write, right?
Exactly.
So now the view that you will have of the page tables have maybe bits that are set differently than what they would be if you really had a clean copy of the page table 3. Have you is this a problem, or have you seen it in action?
So we haven't gotten to the point of such granular detail for exploring, but that is one of the things that we will be cautious of in the future.
But actually, to some extent, that's actually what we want, at least as a one hypothesis, right? Because what we're interested in is a view not actually of the page table, although that's what we illustrated. What we're interested in is the state of the memory and registers in a lightweight. So rather thinking of it as a fork, it's a mark. I just want to very rapidly mark that if I ever do want to go back to that point in time, I could get to see the memory state. So in reality, it's the underlying pages. So now, of course, the trade-off between there's overhead, of course, associated with flipping the copy on right, which is going to induce overheads on the parent. So there's going to be a bunch of trade-offs. But in time, as you're pointing out, we can delve deeper in. Like one of the values of
it's a really good start. I mean, it's a really good starting point. Be aware of the next thing that you really want to do differently. For example, anything has to do with shared mappings, right?
Yes,
That get propagated through, and that's going to be an issue.
Yeah.
Excellent question.
So I was thinking that you have a very impressive piece of machinery.
During the system,
Have you considered instead of figuring out when you can actually copy the process to take a snapshot, just doing a a little patch on your system call table of the process you want to monitor. So whenever its parent is gonna call fork, it doesn't call fork because your fork, which does the copy process, takes a snapshot, and then everything else, runs by itself.
So just to clarify, are you saying that when the original process that we want to fork calls fork, it doesn't actually call fork, it calls Arbor?
Which is gonna be patched to call fork, do your stuff, then exit.
That is cool, but the whole point is that we want to be able to fork it without it ever knowing that it got forked, and at the points when it didn't even intend to get forked.
Oh, okay.
So, like, one of our examples was just a simple spinner program. It's just a while true loop that runs, and when it receives a signal, it gets some amount of memory, 1 megabyte gets allocated. It never calls fork itself, but we want to be able to capture its state. So you create this other branch in the timeline that creates a copy of it.
Okay, understand.
Sometimes you can think of it that fork just happened to be there going, that looks an awful lot like what we want.
Oh, yeah,
Right,
but it's not that
traditionally,
you need a fork to be there.
yeah, but traditionally Unix, right, or Linux, Unix, it's horrible over that notion, right? Fork is such a pain because it's only relative to who I am,
Yes.
not somebody else because of the poor design of the kernel.
Yeah.
In my humble opinion.
Yes, sir.
I think the pro and con of your approach is letting Linux take care of fork, right? Like the fact that you don't have to think about all of the work that it's doing to duplicate all of that kernel state, right?
Yeah.
That just sounds great. Then on the other hand, you're putting all of that on your critical path of your snapshot mechanism. So these gather steps where you go through and for each file descriptor, for each thing that the OS is tracking, right? You're taking on those costs, right? And when you deploy them, the whole other side of the scatter, right? So in the Suits paper, we argued that overhead was exactly what we were trying to eliminate. So I think one cool thing that could come out of this is just to get some ground truth on that. Like, is that actually the cost? Because it was really speculation for us. The only other comment there is this like copy on write. I thought it was just a real neat, like, oh, everything's copy on write. It's really lightweight. Turns out like it might even be the minority of your state that gets marked copy on write. A lot of it gets done eagerly. So there are some expenses to think about there for like larger processes.
That's an excellent point. And since this is just a prototype, we wanted to go down the easiest road. So being able to reuse, and one of the biggest advantages of dynamic privilege and K-Elevate is that we're able to reuse a lot of the code that's already in the kernel without having to rewrite a ton of that code. So we wanted to find the golden mean, like where we can extract the most out of the kernel without rewriting it, but also have as much of control over what happens as possible.
And you have the opportunity to put unit kernels in your process, and then it's still encapsulated in that space and might still be really lightweight.
Yeah. So going forward, we are going to be looking further into ways to further control it and obviously optimize, make it more efficient, but also reuse as much code as possible.
And not to mention, like, although we intercepted and we talked about it like we were intercepting it as fork, the truth of the matter, it's kernel clone, right? And the Linux clone call is so configurable and rich. And partially I didn't want to think, right? So we just stole the easiest path forward. That's right. So we stole the easiest entry point was to simulate fork first, and then start to go down and pull the pieces apart.
Does that answer your question?
So I don't suppose you want to comment on the fact that your supervisor wrote a paper that says fork is a terrible abstraction that compromises OS implementation. Just.
I stand by that.
I'm here to talk about ForkU.
I guess,
Yes.
I was wondering, like, what kind of mitigation strategies would you think of addressing things like IO and stuff? Like what are some things you're thinking about?
That is excellent point. We're getting to that now, and we're starting to understand like what state the process has to be in. And obviously, the ideal world is we want to be able to snapshot and fork any arbitrary process in whatever state it's in. Even if it's a multi-threaded program, Mcached maybe just snapshot at different points, but it's a long road to that.
External
But the
IO, it gets kind of.
But to some extent, Han, that's exactly, so while we're, right now, Albert's talking about what can we do safely, right, the way it is. But the truth of the matter is, with dynamic privilege, we can go in and first call much lower level routines. Secondly, we can put things into the state, right? So fork is designed to be called from the thing that's currently running.
Yep.
But we're the kernel now.
Yeah.
So we can literally not make it running, go underneath it. I mean, it's just that right now, the simplest way into it is just first figure out, hey, what are the safest regions that we can use the highest level routines, and then go deeper.
In other words, say ForkU to the application.
You didn't notice.
To touch on both of the questions, I'm gonna be a little annoying, but is it possible, like, the way you set things up, can you snapshot the snapshotting process?
Yeah, so originally, one of the first prototypes of the snapshotter was to actually, instead of giving it a PID and snapshotting other processes, it was just trying to read its own page table representation. So absolutely, you can.
So to that end, then, Tommy, I guess they can work on the remedying the long paths that you're talking about.
That'd be cool. So this is really cool, primitive, and explaining it. I'm just curious though, you're also like that. So looking at the kernel data structures and being able to visualize them in interesting ways, does that, can you also do that for a running, like, do you created a snapshot and then did that on that data structure?
No, actually, his first examples were just on normal running processes.
Okay, so it's not like that depends on this. That visualization of the stuff can happen just fine without this snapshot.
Right, exactly, because it's, as we know, it is safe so far with the stuff we tested.
Let's be careful with the word safe. So what we know is that you can go ahead and peek into a process. If you want to put that process into sort of a known state so that it is safe and interpretable, great. And if you don't, great. Right, and so for the moment, we've separated that out, and it's up.
Yeah.
And because there's already so many things in Linux, why should we go and force a particular no, it has to be a stopped process. Instead, if you want to stop it, and then look.
So for the next step, since you're talking about exec-Q, right? So you know already that when you do an exec, you kind of do a fork and then you replace the addressing space. You could take a look at that kind of routines to basically replace the running context of a process.
Yeah, exactly.
And the nice thing about exec-Q is, so we usually think of exec right from giving an L file, right? And what we've got now, and because these are the full, as Tommy was mentioning, right? Because we did fork, right? The doppelganger has associated with it still an L file somewhere, right? Because it actually still has the original, it's got an attachment through its page table mappings and through its VMAs.
Do the bin format params carries over? I don't think so, though.
Well, so the VMAs still actually point you for the read-only sections
for sure.
to the ELF, right? So we've got this thing, and now we're basically asking more generally, hey, can you take a process and create a new process from it that's not really attached fully to that ELF file, right? It can be actually synthesized, and so it's this really interesting thing that exec-U is really going to move exec from it being about ELF files to being about process states.
But already, if I'm correct, it's been a while, I haven't looked at that code, but I think the exec already assumes a task struct because the exec enters after the bin loader, the binary loader. So that already kind of has the same model, but
right, but usually when you do, so so that's the whole split, right, in Unix, fork exec, fork gets you the task strap, exec replaces the current image with that, so, but now our image, in some sense, is this lightweight. Like, we're gonna be spawning a third process, right? It's not, we're not taking the doppelganger and running it.
Which doesn't depend on the binary external
Ex-
file, for sure. You can shortcut directly to the exec
Exactly.
without the bin loader, the binary elf loader, yeah, for sure.
But we can also modify.
But actually, sorry, what get me thinking from what you just said is actually, can you actually produce an elf with an intermediate?
Exactly, so then the next thing is that you will now create a new tree
Sort of like.
that are these trees of processes who you can then pull back out as an elf file.
Yeah.
I actually talked to Uli about that a long time ago.
Hopefully, I mean, glibc would give you a hell of a nightmare on that, but yeah, in theory, yes.
I might just add a comment if it helps anyone imagine into how you'd use this, right? Like snapshotting is a pretty general technique.
Yeah, well, it's
Right?
theory.
Like you can use it to do a long initialization process and then grab it and then deploy from that point. It can be used for memory sharing, where across a bunch of these environments, you have copy on write references backwards. You can also use it for like analysis, as he showed us, but also for
you grab your state right before your program entered an error state, and you can replay that over and over again. You can
And I share my presentation over here? Yeah. Got it, okay.
That's great.
Do you have USB-C? Yeah, I know. Just gonna. And then you might have to go into the whole. You click start video, and then we're just gonna make sure we're hooked up to the room. So if you click on that, and it's extra on media port, and then same thing for the audio. Got it. Echo count.
Are you monitoring the chat?
There was a second speaker, so the chat was just saying I lost live.
I think we need to.
So I think it's great.
Floating panels. No, not that. Can somebody introduce something or?
I think I'll just get started with this.
Okay.
Okay. Hello everyone, I'm Pranav and I'm going to be presenting my research on improving software composition analysis tools through the use of threat knowledge graphs. Technical issues. Okay, now. Okay. So the agenda for my presentation is I'm just going to provide a bit of background on what the motivation for this particular project was, the recent efforts I've made over the past 3 months, as well as the future steps that we're going to be taking going into this semester. So the motivation was mainly dealing with the third-party open source code that many companies use in their production software. So according to a 2023 annual open source security report by Synopsys, nearly 96% of code bases in industry use open source code. It's such an integral part of the software development process, and over 84% of them contain at least one known open source vulnerability. Now, software composition analysis is a security process that automates this process of open source component management. Now, SCA tools, they can provide several features. Some of the tools that were part of our analysis, they provide things such as vulnerability detection, vulnerability mitigation, and license compliance. They will typically scan the code, and then they will show the existing vulnerabilities, and they're listed as the common vulnerabilities and exposures, CVEs. So people who are familiar with the way NVDs work, with the way the NVD works, the National Vulnerability Database, will know that common vulnerabilities and exposures, kind of the way we talk about vulnerabilities. To assess and mitigate these vulnerabilities, these tools can often provide additional information. By selecting and looking at the commonly used SCA tools in industry, we wanted to determine which areas can be potentially improved by integrating them with threat knowledge graphs. So the tools that we selected for evaluation were Snyk open source, which is a tool that's provided by the company Snyk and is a commercial tool. Mend SCA, which is also a commercial tool that's provided by a company that was formerly called White Source. Now it's called Mend. GitHub Dependencies Graph and Dependabot, which is a tool available through GitHub. OSD Scanner, which is an open source tool that's been developed by Google. And Red Hat Code Ready Dependency Analytics, which is a tool developed by Red Hat. So the way we went with it is first we performed a workflow analysis to get an idea of how all these different tools work. We utilized an open source project called Zero Code, which used the Makefin package manager to manage all the dependencies. Unfortunately, MendSCA did not have a free version, so it's not part of the workflow analysis, but it was included as a part of our qualitative analysis that was done later. Some sample outputs of the tools are shown on subsequent slides. So this is kind of how the Snyk open source tool, the output looked. So Snyk open source is available as multiple integrations, and we use their web application for our testing purposes. GitHub Dependencies Graph and Dependabot is only available in on GitHub, which means that you have to use GitHub and integrate your repositories to be able to use the tools. And this is kind of how the output looks. OSD Scanner is available as a command line tool. So this is how the output looks in the command line. And a Red Hat Code Ready Dependency Analytics, it is available as an IDE extension. So this is the VS Code IDE, and this is how the output looks in there. So the key results from the workflow analysis were, first of all of these tools yielded a different number of vulnerabilities. Snyk open source had detected 58 vulnerabilities, whereas GitHub Dependencies Graph and Dependabot yielded 24 vulnerabilities. There's inconsistency in the way these tools detect vulnerabilities. Moreover, these tools also differ on, report different results for the same package being vulnerable. For example, for the dependency, com.h2 database, GitHub and OSD Scanner uniquely identified this as vulnerable. However, open source and code-ready dependency analytics do not identify this as vulnerable. For the vulnerabilities exclusive to Snyk and Red Hat report different results. So one thing to keep in mind is the vulnerability database that each one's used. So Snyk and Red Hat Code-Ready Dependency Analytics actually use the Snyk Intel vulnerability database. And despite the fact that they use the same database, they were showing different results. For the same vulnerability, different tools report different severity scores. So from this, we were able to formulate a number of key takeaways, which will be the focus of our research going forward. The first one was the discrepancy when it comes to the vulnerabilities reported. For certain dependencies, which means that these dependencies were detected as vulnerable for all the tools, they reported different number of vulnerabilities within them. Secondly, Sneak open source and Red Hat Code Ready dependency analytics provided an easy way to visualize vulnerabilities through transitive vulnerabilities. They provided a way for you to view exactly what transitive dependency introduced a vulnerability into a particular dependency, which GitHub Dependabot and Google OSV were not able to, which is a very important thing, which I will bring up when our feature works. Tools utilizing the same vulnerability database reported relatively consistent results. We were able to form two kind of ecosystems of OSV Scanner and GitHub Dependabot that kind of use the same database, which is the GitHub Advisory Database. Whereas Sneak open source and Red Hat Code Ready dependency analytics, they use the same Sneak Intel vulnerability database. So within these two ecosystems, we saw consistent results. And when you compared them, we saw different. So one thing we realized is if you're a software developer, you might want to consider using tools from different ecosystems to be able to get better results. The tools also differentiated in the way they reported vulnerability severity. So GitHub Dependency Graph reported NVD CVSS scores, whereas Sneak reported their own CVSS scores, which can be a huge difference for certain vendors, because certain vendors will only mitigate vulnerabilities that meet a particular severity threshold, for example, medium, high, or critical. So if you have tools reporting different severity thresholds, you don't exactly know which one to take. Now, as for the qualitative analysis of the tools, we wanted to generate a sort of guide onto what kind of software composition analysis tool you may want to pick based on your use case. So the evaluation criteria that we selected were the software development lifecycle integration that it provides. How well does it integrate into your CI/CD pipeline? How well, what kind of, is it available as a command line tool? Is it available as an API, a web application? What vulnerability library does it use? So in the sense of, does it use the Sneak Intel vulnerability database? Does it aggregate databases, or does the database that it uses actually have its own research? For example, the Sneak Intel vulnerability database, it has its own security experts do research to find vulnerabilities. But the GitHub Advisories database is simply an aggregation of vulnerabilities from different sources. Automatic remediation. So certain tools will have the ability to automatically open up pull requests and automatically provide fix advice for certain vulnerabilities. For example, Sneak and Red Hat Code Ready dependency analytics, as well as GitHub. However, OSV Scanner does not provide that functionality. So as a developer, if that's something you find useful, that's something you should know. Security report format. So this is more so of how you want to, whether or not you want to integrate this into further steps down your pipeline. So for GitHub, as well as Sneak Intel vulnerability database, they do not let you generate your output in the form of a JSON file, but OSV lets you output it as a JSON file in case you want to perform further analysis and run it in a particular format. Finally, availability, open source versus commercial. OSV is the only open source tool here, whereas all of the other tools are commercial. And depending on your particular use case, you might prefer an open source tool. Finally, language support. We came up with our own benchmark because we didn't want to just list out how many languages they support as is. Instead, what we did is we used the Stack Overflow survey on the 10 most commonly used languages and the 5 most commonly used package managers. And based on how many of those they meet, we assign them a score. So this is a table showing the kind of comparison of the different tools and how well they work. So I can walk through the table quickly, but as you can see, Sneak and MEND-SCA, which are two of like our commercial scanners, provide the most SDLC integrations. Vulnerability library, Sneak and Red Hat use similar ones, whereas OSV and GitHub, the GitHub Advisory Database and the OSV database, they are very similar in the sense that they both aggregate from the same sources, and the OSV database actually aggregates from the GitHub Advisory Database, which explains why there was so much similarity between their results. Automatic remediation is offered by all the tools except for OSV Scanner and Red Hat Code Ready Dependency Analytics. OSV Scanner and Red Hat are the two open source tools. And as for language support, As you can see, the languages that we considered were JavaScript, Python, TypeScript, Java, C#, C++, C, PHP, Go, and Rust. And based on that, we've assigned a score out of 10 to each one of the tools. One thing that we learned going through this was actually the fact that even if a particular package manager is supported, that does not mean that a particular language is supported. For example, some of the tools that we were evaluating supported Maven, but they did not support languages. The difference between this is the tools that support the Maven package manager, they detect vulnerabilities using artifact IDs, whereas the tools that have the ability to detect vulnerabilities based on language, they use jar files, and they have a better way of resolving particular vulnerabilities. So based on these, we were able to come to the conclusion that if you're looking for a feature-rich tool, then Snyk open source and Mend SCA are probably your best choice. However, if those aren't necessarily what you want, we got similar results from Red Hat Code Ready Dependency Analytics, as well as the free version of Snyk open source, if you do not require all that feature richness. And finally, if you need to use a free tool, then OSV Scanner is very intuitive, lightweight, and it's open source, which was one of its strengths. So based on this, our conclusions were that there's a lot of difference between these SCA tools that are available, and a lot of developers use them, and a lot of developers don't necessarily know how they work under the hood, and the companies also don't try to make it very easily understandable. So if software developers want to adopt these tools, it might be better for them to adopt multiple tools and be able to take advantage of different ecosystems that they belong to. And future steps for our research is one thing that we repeatedly encountered while we were doing this was the issue of false positives. So SCA tools can sometimes report vulnerabilities in dependencies that are not necessarily there. They can misidentify whether a dependency has been included, or even worse than that, a vulnerability may exist in a dependency, but that dependency may not be used in a way for that vulnerability to be exploitable. And it is very hard to determine that latter fact, whether or not you are using a dependency in a way that is exploitable. It can waste a lot of time and can send you on wild goose chases. And developing a standardized way to get a quantitative evaluation of these false positive rates of SCA is something that we feel like is a very important important thing we want to do in the future, because we want to be able to benchmark their claims. A lot of these tools, they will discuss different methodologies. Like for example, Google OSV has an experimental call stack analysis, which will check if a particular function is called. So instead of just basing it off of dependencies, you can go further and see if a particular function is called. But even then, false positives are pervasive in SCA tools, and it's important to be able to figure out how pervasive they are for certain specifications. Secondly, utilizing the transitive vulnerability data generated by SCA tools in form of SBOMs. So SBOMs, software bill of materials. SCA tools can generate a detailed list of all your important dependencies. And what we noticed is the performance of SCA tools on a SBOM that's been generated using a Maven plugin versus the performance of SCA tools simply on the pom.xml file vary differently. And it has to do with the development of this the transitive dependency graph, which SBOMs provide a better way of developing it for these tools. So because of that, what we visualize for our project going forward is to leverage these SCA tools to develop detailed SBOMs as well as vulnerability information to create a threat knowledge graph for a project, which integrates into a bigger knowledge graph. So the way we want it to work is, say you have a bigger project A, and you have a project B that depends on A. Right now, the way SCA tools are used is you would have to run SCA analysis on project B and project A and wait for new vulnerabilities to pop up on your analysis. Instead, we want to be able to form an ability for you to query the knowledge graph saying this new vulnerability was detected. Do any of our current projects in development have this vulnerability within them, and use our data that we've generated from SCA tools that have already been running the past to be able to quickly identify which projects might have that vulnerability. Another important thing with this is for companies, they may not have easily resolvable dependency graphs. For example, let's say you have project A, project B, and project C. And project A imports certain dependencies, and then your project B and project C depend on project A. When you run SCA analysis on project C, if you're just importing your project A, it will not have the entire dependency information for project C. So we want to be able to create the system where with threat knowledge graphs, where if you can basically run SCA analysis once, store it in your threat knowledge graph, and then be able to query your knowledge graph for new existing vulnerabilities by paying attention to vulnerability dashboards and being able to see how far it affects all your projects, which particular products are exposed to that vulnerability, as well as leveraging other information that you receive from SCA tools regarding fix advice, severity, threat, to be able to see whether this vulnerability should be prioritized or not. That's all from me. Thank you.
Chris, I really want to commend you on doing a real data-driven approach to trying to understand some of this stuff, because oftentimes it feels so nebulous, and to go and actually do some analysis is fantastic. So I'm curious about a couple of things.
Yeah.
So that one point that you had mentioned in your future work, right, about wanting to be able to target the false positive rates and so on. So it seems to me that in general, with a lot of this stuff, there's a lot of big questions about human factors and HCI in terms of the people who have to consume this stuff in a meaningful way, right? Because I often worry and wonder about if you took the total cost of ownership for a company, right?
Yeah.
As you pointed out, every false positive costs time, effort, and money to go pursue, which also means that there's a big economic denial of service attack just waiting to happen, right? We all depend on open source software. I purposely go out and I make sure that I make it seem like every damn thing has a vulnerability in it, and I can send off many companies into la la land chasing their tail, right? So there's like, as we grow these tools, the specific vendors have very little advantage in addressing some of those problems. And I think benchmarking and the ability to actually quantify and filter this stuff is going to become radically important. But I was curious, from that perspective of the HCI front and how people consume this, is there work in that space? Like, how do you get real knowledge about the effective feedback that these tools and meta tools are going to have to provide?
Sorry, I just wanted to ask what HCI stands for.
Oh, human-computer interaction. So just in general, this idea of how does the human consume all of this data about these vulnerabilities and the graphs? How do we make use of it in a meaningful way without feeling like overwhelmed?
Yeah, so alert fatigue was one of our major reasons of kind of pinpointing the false positives, because when we were reading reports, we read about just how expensive it is to send. Most developers actually said that they found it more challenging and harder to find a false positive, to properly investigate a false positive, than it was to properly investigate an actual vulnerability. So with all these, that's kind of why we want to work on a threat knowledge graph and kind of put all this information in an easily variable way, because we want to reduce how much time, because as I was doing this analysis myself, I was looking at just lines of information, a lot of package information, a lot of things, trying to figure out which vulnerability mattered, which didn't. And it is frustrating, and it is also time consuming. The threat knowledge graph is kind of trying to bring that down, because what we foresee with the threat knowledge graph is also incorporating LLM techniques, because a lot of the NVD entries for particular CVEs are very useful. They contain a lot of information about how to mitigate them. Some CVE entries that I saw even talked about the particular way in which this would be exploitable. One thing that we were talking about is dependency may have a vulnerability, but it may not be exploitable unless it's, let's say, used on a Linux system or used in a particular environment. So we want to leverage AI and LLM to be able to kind of give that information to the user without having them have to chase down all of those things.
Hello. I assumed that this was all static analysis, but you mentioned this like stack-based call chain thing. Is that like simulated or is that actually a runtime or?
So the experimental stack analysis from so all of the SCA tools are static. All of them read the so we were using Maven, so all of them read the pom.xml file to determine the vulnerabilities. So they will build your dependency graph based on the artifact IDs. You can also use SBOMs for that. So the experimental call stack analysis from Google OSV, they're working on it. It's not complete. So when I did enable it, I don't think it actually worked because it was giving similar results, and nor did it ask me to run my project or build my project. So it's currently in its experimental phase, but it's something that we do want to investigate once we see that like they've made more progress on. Cool. Yeah, thanks.
So, okay, so a lot of these things get go to the vulnerability database and they tell you, in your knowledge graphs, this is to represent the relationship between everything, which isn't represented today in those vulnerabilities. Is that correct, my understanding?
Yes, so currently one of our future directions is like it is forming mappings. So there's multiple different information metrics. There's CPE, common platform enumeration, CVE, common vulnerabilities and exposure, and then CWE, common weakness enumeration. And our knowledge graph, we foresee like being able to form mappings and relations between these different entities to provide like more information to the users without having them have to chase down those particular things on their own.
Yes. Okay. So I guess these. So I was just poking around, so like that Red Hat tool, it is open source, by the way,
Yeah.
but it's actually embedded into Visual Studio, just so it's to be used. What are most of these used today just as a part of some development platform that way, or?
So yeah, so I think I have that on my SDLC slide, so I'll just bring that up. So in particular, like the Sleek open source tool is available as a command line tool, web app, repository integration, and IDE plugin. Moreover, if you want to use the commercial tool, you can actually have it be a part, you can deploy it on the cloud and have it be a part of your CI/CD pipeline. So different tools, depending on like what their particular use cases, have different integrations. So OSV Scanner is exclusively available as a command line tool, or it has an API that you can query, but you can only batch query it. And Red Hat tool is only available as an IDE plugin.